at, Jared recommended that we try 1 over a squared minus bx squared dx. And so we'll try it first with partial fractions, and then we'll try it with trig substitution and see what happens. So with partial fractions, we would consider that 1 over a squared minus bx squared can be factored in the denominator as a minus bx times a plus bx, right? It's the difference of two squares. And then that is going to be equal to capital A. Now we have capital A's and lowercase a's, so we're going to be really careful. Math is case sensitive today. Plus capital B over A plus BX. And so Jared had noticed that A and B came out with an interesting pattern because this came up in the homework, and they were so he would see things like 11 squared and 12 squared and 13 squared and 7 squared, and he found an interesting pattern with what happens with A and B. So I'm just going to try and do it in general here and see what pops out. So let's see. Clearing the denominators, what do we get? We get 1 on this side, and then A is going to get the opposite denominator, like we saw the other day. So that's going to be an A plus BX here. And B is going to get the opposite denominator, which is A minus BX. Convenient X values are kind of a pain in the butt here, so we're going to take the other approach by distributing the capital A through and the capital B. And again, case sensitivity. Next thing we want to do is combine like terms, so the x's together have an capital AB and a minus big B, B. And then the other two are just big A little a plus big B little a when I bring like terms together. Now notice on the other side of the equation we have a 1, but there is no x term. So I'm just going to write it as 0x. So what that tells me is that this has to be 0, and this has to be 1 when I compare sides. So that gives me my system of equations. Let's go back to blue. So big A, B, minus big B, little b, has to be 0. And big A, little a, plus big B, little a, has to be 1. So here, since we're almost done with this part, so we'll get rid of the cases in a minute. So here, since there's a 0 on the other side, I could add the big B, little b to the other side. So I get A, little b equals B, little b. And remember, we're trying to figure out what the heck A and B are. So for example, I want to solve for that big A there. So I would divide both sides by little b. That's nice, isn't it? That tells me that capital A has to equal capital B. So if I substitute that into this equation over here, so I can replace capital A with a capital B, so I get capital BA plus this capital BA equals 1, which means I have 2 capital BAs equals 1. And remember, I'm trying to solve for big B. So to do that, I just divide by 2 little a. So I get big B is equal to 1 over 2 little a. So now I know my coefficients. A and B have to be the same. B has to be 1 over 2 little a. So that means A also has to be 1 over 2a. Since they're common here and here, I can just factor them out. So here's what I think I have. New page, switch back to black. I started off with the integral of 1 over a squared minus bx squared dx. And now I have the integral. Now keep in mind, both a and b are 1 over 2a, so I can factor that out of this sum here. So I'm just going to pull that out here, 1 over 2a. And then I have the sum of 1 over, let's see, which one did I put first? The minus a minus bx plus 1 over a plus bx. So there were a couple of homework problems like this, but they didn't state A and B. They stated like you would see like a 121 here and maybe a 64 there, something like that. Antiderivative for 1 over a linear function. ln. Now there's a catch on our ln here, so we'll have to be careful. 1 over 2a is out front. Oops, that was supposed to be a 2a. 2a. And then inside, I think I have the natural log of the absolute value of a minus bx. Catch though is, what if I take the derivative of the natural log of a minus bx? What's going to happen? Well, derivative of the natural log is 1 over, but the chain rule says you have to multiply by the derivative of the inside. What's the derivative of this a minus bx? Do we have a negative b here? No, so we have to compensate here by multiplying by a negative 1 over b. You're running out of it, lead? Okay, I got a pen here if you need it. Similar on the other side, derivative, the antiderivative here is related, so we're going to have a natural log of the absolute value of a plus bx. However, when we take that derivative to try and get back here, we will get 1 over, but the chain rule says we'll have to multiply by the derivative of a plus bx, which is b. I don't have an extra b here, so I have to compensate by multiplying by a 1 over b. Now notice we have a 1 over b in both of those, so I'm just going to shuffle this a little bit. So I'm going to pull out a 1 over b and change the order, because notice this one's negative. So I'm going to write that one second. So I'm going to write this guy first. So I have a natural log of the absolute value of a plus bx. Then I have a minus the natural log of the absolute value of a minus bx. And I pulled out the 1 over b. So now I have a 1 over 2ab. And that's the thing Jared noticed. He noticed that you would get 1/2 of the reciprocal of ab every time you did a problem like this as a constant multiple, which is kind of cool. That just pops out like that. And we can clean this up further, right? Because we have a rule that says if we have the difference of logarithms, that's the log of a quotient. So I get 1 over twice ab times the natural log of the quotient of a plus bx over a minus bx. So that condenses pretty nice. So if you're bored this weekend, what you could do is take the derivative of this guy right there, and what you should find is it will clean up to be that in the end. Now doing that, you'll have the derivative of the log. Inside the log, the chain rule says take the derivative of this fraction, so you have to use the quotient rule. Inside the quotient rule, you'll have the derivatives of each of these guys, so it's rather a complicated derivative because it's functions within functions within functions there. Ooh, that was exciting. All right, we're going to try it again, but this time we're going to use trig substitution. Review that. And that's one of my favorites. I like trig substitution way better than partial fractions. But partial fractions are cute too. Unless you guys want to do a partial fraction problem. Do you have one you want to do from the homework? Yeah. Yeah, there's some problems at the end involving what are called differential equations, which I've been avoiding. Yeah, so you can just skip those. Jesus, did you have any kind of problem you wanted to do? Partial fractions versus trig substitution? Do some more of that? Okay. Let me do a trig substitution, then we'll do the word problem. So integral of, we're going to go back to the same antiderivative, a squared minus bx squared. But this time I'm going to use trig substitution to solve it. So with trig substitution, that's useful when you have something like an a squared and an x squared plus or minus. So we're in a good place to do that. So first step with trig substitution is to draw a triangle. Label your angle. The a squared has to be the hypotenuse because I'm subtracting a square from it. So a has to be there. And then if the x isn't on the hypotenuse, we prefer it to be on the opposite side. So then there's going to be a bx here. And the other side is going to come from squaring the hypotenuse and subtracting the square of the other leg, and then taking the square root of that. So there's my adjacent side. So sine is opposite over hypotenuse. So bx over a is equal to the sine of theta. To get the x alone, let's see, do I want to get the x alone or I want to leave it there? I think I want to get it alone because I need a dx. So x would be equal to a over b times the sine of theta. And then differentiating, I get dx is a over b times the cosine of theta. So I've got my dx, I really need that here. Oops, I missed my d theta, didn't I? D theta. Then I got to get this guy down here, which is going to be the square of the square root. So first, note that the square root is going to be the cosine over a. So that means the square root of a squared minus bx squared is going to be equal to a times the cosine of theta. Now I want the square of that for my denominator, so that means a squared minus bx squared, the inside of the root, has to equal the square of the other side, which is a squared cosine squared. And so now I'm ready to substitute because I have my dx, and now I have my denominator. So rewriting that, let's do it in blue. So this should be equal to 1 over a squared cosine squared. Let's see what else. And then dx is a over b cosine of theta d theta. And that cleans up nicely, doesn't it? Cosine, one of the cosines canceled. An a here in the top will cancel with one of the a's in the bottom. So I can pull out here a 1 over ab, kind of similar to last time. And then what do I get? I get 1 over cosine d theta, which I can also consider to be the secant. Anybody remember an antiderivative for secant? I think it's natural log of secant plus tangent. Double check. Integral formulas. You got it written there? Okay. This, I just found this website last night. They claim they have, oh no, 3 million integrals served. I thought it said they have 3 million integrals in their table. Like, what? That's crazy. Okay, no. It's like, really? Wow. Yeah. All right, let's get back here. All right. Yeah. So, yeah, Wikipedia's got a lot of good stuff. So this is the natural log of the absolute value of the secant of theta plus the tangent of theta, and then plus c. Now we got to translate secants and tangents back to x's. So we got to look back at our work over here. So let's see, what do we got? Secant is 1 over cosine. So if cosine is the square root over a, secant should be a over the square root. So that's going to give me, let's switch back to black here. AB, natural log of the absolute value, secant, according to my triangle, is a over the square root of a squared minus bx squared, plus tangent is opposite over adjacent, so that's bx over. So bx over a squared minus bx squared in the square root. And somehow that is equal to this. So let's see. I'm just going to clean it up a little bit and see what happens. How about new page? I have a common denominator there, right? So we can add the inside. So I have 1 over AB on the outside, natural log, absolute value of a plus bx over the square root of a squared minus bx squared in the square root. A little better. Oh, this, do what? Yeah, but that we would have to separate this as a difference to do that. Oh, that might work. Oh yeah, check this out. Yeah, there's a couple things we could do. All right, so if I rewrite this, I get the 1 over AB hanging outside, and then I'm going to break this division as a difference. So that would be the natural log of the absolute value of A plus BX minus the natural log of the square root. And like you said, the square root is the 1/2 power, so we can pull out that 1/2 power. And that's going to give us then the natural log of the absolute value of a squared minus bx squared. Now, a squared minus bx squared is really a minus bx times a plus bx, right? And what can we do with the product of logs? We can add them, add the logarithm separately. So I still got my 1 over AB out here. Now this is all unnecessary. I think this is a very happy solution right there. I'm just trying to show it's equal to the other one, right? So this is just an exploration. So a plus bx. Now I'm going to have a minus 1/2, the natural log of a minus bx. And then when I separate this product off as an addition, I got to distribute the minus 1/2 to it. So I'm also going to have a minus 1/2. All right, yeah. Natural log, absolute value of a plus bx. Close parentheses plus c. All right, we're getting close. If I have a whole natural log of a plus bx and I take away half of a natural log of a plus bx, what's 1 minus a half? A half. So then I'm going to get a 1/2 when I combine this with that. Natural log of a plus bx. Chilling out here is the minus 1/2 natural log of a minus bx. We can pull out the 1/2, and then we'll have a difference of 2 logarithms, which is a quotient. So I think we just got what we did before. So I have a constant of a 1 over 2ab, And then the difference of these two logarithms becomes the log of the quotient of a plus bx over a minus bx, which is exactly what we had on the other page. And sometimes it's not bad doing algebra to show two equations are equal or different by a constant. Sometimes it is. It just kind of depends. This was kind of in the middle. It wasn't too bad. It wasn't too easy.
Prove that this number is, prove that this math's right. Because 4 plus 4 is 8.
Draw a picture of 4 and another picture of 4. That's a proof. All right. Let's take a look at was it at the end there was a story problem? Okay, so this is 8, 4. Yeah. Let's try 27. Yeah, so this is what's called the differential equation, which isn't that bad. I chose to skip them this term. I might do them next term. This one. This is a good one. Yeah, should we do a volume? Sure, why not? Okay, so let me borrow this to my notebook. Let's get a new page. And we'll just have time to set it up. We're not going to have time to finish it. Maybe, we'll see. Oh yeah, eraser now. Yeah, I try to do math in pen, so I don't erase something that was actually good. All right, so let's think about this. Find the volume of the solid by revolving around the x-axis. So I want to draw that in. So I'm revolving around the x-axis. All right, so my opinion is I probably should use shells. No, discs. Yeah. So I'd have little rectangles like that to run around. Yeah. Yeah, shells would be very awkward here. Oh my, yeah. Yeah, shells would be wicked awkward here. We don't want to do that. Because we'd have to break it into, oh no. It does look a little like the Koch curve, yeah. Yeah, there's a lot of curves that have that parabolic kind of shape. The Koch is one of them, and there's a gazillion others. All right, so to do that, so that means when we revolve this around the axis, we're going to generate these disks, micro thin disks, and we need to identify that radius. And the radius here is just the height of the function. So our function y equals is our radius there. So that's pretty straightforward. So we're going to calculate the integral of pi r squared dx, where r is that function. So that's going to give us, let's see, the integral of pi times the square of that. So I'll give a 36 on the top. Square root goes away in the bottom, so we just have 6x minus x squared dx as x goes from 1 to 5. Denominator factors, so let's ignore the integral for a minute and just deal with this fraction. Sometimes the constant that's given is relevant to finding a nice neat a and b, and sometimes it's not. So I usually put it in there to start with, and then if it looks ugly, I pull it out later. So I'm gonna leave the 36 in for now, but I'm gonna factor the bottom as x times 6 minus x. And then I want to find an a for over x and a b for over 6 minus x. Multiplying through by the common denominator, x times 6 minus x is going to give us 36 equals a times 6 minus x, because the x cancels out, plus b times x, because the 6 minus x will cancel with the denominator, right? So keep in mind, we are multiplying both sides by x times 6 minus x, the common denominator. And I think this is a great place to use convenient values of x. So for example, if I let x equal 6, then this term goes away. So over here, I'll just make a note. X equals 6 gives me that 6b equals 36. And so b has to be 6. And then what's another convenient x value here? 0. If x equals 0, then the b term is gone, and I get 6a equals 36. So that implies a is also 6. So it looks like I could have pulled the 36 out, and then I would have had just 1 and 1 there. Okay, so rewriting, we now have, let's see, new page. The integral as x goes from 1 to 5. I'm going to pull the pi out. My radius squared is now the sum of those two fractions, so 6 over x. Why am I writing in red? Let's fix that. Make it black. And the other one is what, a plus 6 over 6 minus x dx. Let me just look back, make sure I got that right. Yeah, we left the pi out. We kept the 36. Yep, we're good. So antiderivative here, I'm going to pull the 6 out now. So I'm going to have a 6 pi on the outside. And then antiderivative of 1 over x is just the natural log of the absolute value of x. And then here, I'm pulling out the 6, so that's a 1 over. I'm going to have a natural log of the absolute value of 6 minus x. What's the catch here? What's the derivative of 6 minus x? -1. Is there a -1 sitting here? No, so we have to compensate by putting in a -1, which is going to make that a minus. And we're evaluating that from 1 to 5. Now we could rewrite that if we wanted to. You could also say that 6 pi times the natural log of x over 6 minus x. And that's being evaluated from 1 to 5. And I guess if you can get away with less natural logs, you're better off. All right, so that gives us 6 pi times, if we plug a 5 in there, we get 5 over 1, so the natural log of 5. And then we'll have a minus the lower bound. And so what do we get there? That would be 1 over 5. And I can actually clean this up a little more. Just note that the natural log of 1/5 is the same as the natural log of 5 to the -1, which is the opposite of the natural log of 5. So so really the natural log of 1/5 is like subtracting the natural log of 5, which is already being subtracted. So I can actually say what I have here is 2 natural logs of 5. And maybe I'm curious if the online homework will take that. And I still have the 6 pi times that. So in the end, it looks like the simplest I can write this is 12 pi times the natural log of 5. I'm going to try and type that into the computer and see what it thinks. Where'd you go, computer? There you are. All right, so we got a 6 pi times parentheses natural log of 5 minus the natural log of 1/5. Close, close. And where's the check my answer button? It's gone. Ah, really? Oh, I clicked review, not do it. Oops, darn it. All right, well, I'm 90% sure I'm right. So to double check, I could just ask Wolfram Alpha. And please don't do your homework just by using Wolfram Alpha. That will not benefit you on the test. So if I integral, oops, didn't mean to hit enter, of, let's see, pi, I'm just going to type it as it was given. The original function was 6 over the sqrt of 6x minus x squared, if I remember right. And I want the square of that from 1 to 5. I think Wolfram Alpha will accept that. That looks correct. Ooh, it got an arctangent out of it. Oh, I bet if we use trig substitution, we get an arctangent out of it, yeah. Oh, arc hyperbolic tangent, yes, an arc hyperbolic tangent is a natural log. Yes, that is correct. Okay, so let me see, just double check our answer. We thought the answer was what, 12 times pi times the natural log of 5, which is 60.67-ish, which is what Wolfram Alpha said with a different antiderivative. But remember, inverse hyperbolic tangent is a natural logarithmic function because a regular hyperbolic tangent is an exponential function. Yeah, cool, that was fun. Thanks guys for playing with me today. Jared, I hoped that playing around with that problem helped you with the pattern you discovered. Talk soon. Over and out. Have a good weekend. Do good math.